picture this for a second. You've got this massive subway train, right? Packed with hundreds of commuters, and it's hurtling through this dark underground tunnel at, like, 60 miles an hour.
Right. High stakes.
Exactly. Or, well, consider a totally different scenario. You have a medical algorithm scanning a super high-resolution MRI, and it's trying to determine the exact microscopic boundary of a brain tumor, basically to guide a surgeon's scalpel.
Oh, wow. Yeah.
Wow.
That is, I mean, that's literally life or death.
It is. And in both of these crazy high-stakes situations, you'd probably assume the computers running the show are operating on, absolute ironclad certainty.
Because that's how we think of computers, right? Rigidity.
Yeah. We have this deep-seated expectation that a machine is just built on a foundation of microscopic switches that are either, like, completely on or completely off.
The ultimate binary universe.
Yeah.
Just 0 or 1. True or false.
Yeah, exactly.
And, I think there is a real comfort in thinking the digital world is purely black and white. But the reality is, well, it's that the most sophisticated systems we rely on today, they don't operate on that principle at all.
Not even a little bit.
No, they actually rely on the mathematics of vagueness.
Yeah.
The digital world is operating in millions of shades of gray.
Which is wild. So if you're listening to this, our goal today for the learner is to kind of shortcut your path to understanding how machines are actually taught to process all this. Because human reality is messy, it's subjective, it's highly imprecise.
It really is.
So we're going on a deep dive today. We have this remarkably comprehensive Wikipedia article on our desk covering a topic called fuzzy logic.
A great topic.
It is. And we're going to explore this whole concept without, drowning you in an overwhelming sea of mathematical equations.
We promise.
Yeah, we're getting straight to the core mechanics of how the world around you actually works.
So to really understand what fuzzy logic is, we kind of first have to understand what it's replacing, right? We have to escape the trap of classical logic.
The Boolean trap.
Exactly, the Boolean trap. Classical Boolean logic is the absolute bedrock of traditional computing. I mean, it relies entirely on absolute integers.
Everything has a box.
Right. Everything must be categorized as a 0, which means completely false, or a 1, meaning completely true. There is just 0 mathematical room for anything in between. A statement is a fact or it is a lie.
Okay, let's unpack this, because I think an analogy helps here. If traditional Boolean logic is a standard light switch like, it's either completely flipped on or completely flipped off,
Yeah.
then fuzzy logic is essentially a dimmer switch. Like, it can be set anywhere along a continuous spectrum.
That's a perfect way to look at it, because in fuzzy logic, a variable can be literally any real number between 0 and 1.
So like 0.2 or 0.85.
Exactly. It introduces this mathematical concept of partial truth. Now, the actual term fuzzy logic was famously coined in 1965 by this mathematician named Lotfi Zadeh.
Right.
But the seeds of this idea, they actually go all the way back to the 1920s.
Oh, really? I didn't realize it was that early.
Yeah, there were these Polish mathematicians, Jan Łukasiewicz and Alfred Tarski, and they were exploring what they called infinite-valued logic.
Infinite values. So instead of just 2 rigid values, you have infinite possibilities between 0 and 1.
Exactly.
But I guess what was the catalyst for this? Like, what was the actual problem with a simple on and off switch that necessitated inventing an entire new branch of logic?
Well, the problem was trying to map human reality onto machine hardware. Zadeh and, his predecessors, they basically observed that humans almost never make decisions based on crisp, precise numerical information.
True.
Like, consider asking a room full of people to identify a specific color, say a particular shade of teal.
Yeah, that's a recipe for an argument.
Right. You aren't going to get a unified binary answer where every single person points and says, that is 100% blue, or that is 100% green. You get a spectrum of subjective answers. One person says, it's mostly green. Another says it's slightly blue.
And neither of them is technically wrong.
Exactly. But classical logic completely breaks down in that scenario because it forces a true or false conclusion on a concept that inherently just lacks boundaries. Fuzzy logic provides the strict mathematical model for that exact human inexactness.
Which sounds like a total oxymoron, like a strict mathematical model for inexactness.
It does sound weird.
I really have to push back here, though, because natural language is incredibly slippery. How do human words, which are inherently messy and totally subjective, literally become math? Because, old to a 10-year-old is very different than old to an 80-year-old?
That's the core challenge, yeah. The translation from human language to machine code happens through what mathematicians call linguistic variables.
Linguistic variables.
Right. So instead of using pure numbers, fuzzy systems actually use words to express facts and rules. They take base words like young or old, and then they modify them with mathematical adverbs.
Right.
The mathematicians actually call these modifiers hedges.
Hedges, like the word somewhat, or rather, or very.
Exactly.
But wait, how can a totally subjective word like somewhat
Opera.
be turned into a mathematical formula? It feels like trying to nail jelly to the wall.
It does. But the process of pinning that jelly to the wall is most famously encapsulated in what's called the Mamdani system.
The Mamdani system.
Yeah, and it works in 3 distinct, highly logical steps. The very first step is called fuzzification.
Fuzzification. I kind of love that word.
It's great, right? So imagine you are programming the climate control system for a massive office building. You define fuzzy sets for the temperature, so cold, warm, and hot.
Okay, simple enough.
Mathematically, these sets are drawn on a graph as overlapping shapes. They might be triangles or trapezoids or even like bell curves. And because these shapes overlap a specific room temperature, say it's 68 degrees, it doesn't just fall into one isolated category.
Oh, I see. Because looking at the temperature example in our source material, there's a vertical line representing a specific temperature reading, and it intersects these overlapping triangles on the graph.
Exactly.
So the red arrow points to 0 for hot. So the machine knows it's definitely not hot. But the orange arrow points to the 0.2 for warm, and the blue arrow points to 0.8 for cold.
There you go. The system is just assigned degrees of membership. The room is 20% warm and 80% cold at the exact same time.
That's crazy.
It is all of those things at once to different degrees. That is fuzzification.
Okay, so that's step 1.
Right. The next step is applying the rules using fuzzy logic operators. Now, in classical Boolean logic, you have logic gates like AND, OR, and not to combine rules together. Fuzzy logic mimics these using what are called zeta operators.
So wait, if Boolean logic uses rigid rules, how do zeta operators handle these overlapping percentages? Like, how does it deal with 0.2 and 0.8?
They use a brilliantly simple comparative method. The fuzzy AND operator looks at 2 overlapping values and simply takes the minimum of the 2.
The minimum, okay.
Yeah, so if a rule requires the room to be both warm and humid, and it's 0.2 warm but 0.6 humid, the AND operator just outputs 0.2. It takes the lowest common denominator of truth.
Oh, interesting.
Conversely, the OR operator takes the maximum of the 2 values.
Makes sense.
And the not operator, which handles the negative, it just simply takes 1 minus the value. So if cold is 0.8, then not cold is mathematically 0.2.
That is remarkably elegant. I mean, it preserves the nuance of the gray area through the entire
It
calculation.
really does.
But eventually, this machine has to actually do something,
Right.
right? It can't just sit there being nuanced.
Right, and what's fascinating here is the final step, which is called defuzzification.
Defuzzification.
Yeah. This is where the system brings all that abstract math back into physical reality. Because a climate control system cannot tell a mechanical fan motor to run somewhat fast.
Oh, right, the motor needs a number.
Exactly. The motor requires a crisp, specific electrical voltage. Defuzzification is the process of getting a single actionable variable out of those overlapping fuzzy truths.
So how does it pick the final number?
Well, the machine takes all those partial truths, so the slightly warm and the fairly cold, and it maps them onto a final output curve. Then it calculates the exact mathematical center of weight of the area under that curve.
Under of weight.
Yeah, think of it like balancing a weirdly shaped piece of cardboard on the tip of your finger. The machine finds that exact balancing point, and the x-coordinate of that specific center point becomes the final single output command sent to the motor.
Wow. So the machine isn't just taking a wild guess. It is literally calculating the exact geometric center of gravity of our vague human intentions to produce one perfect concrete action.
It's beautiful, really. The Mamdani system is deeply intuitive for that very reason. Now, our text does detail an alternative to Mamdani called the TSK system, which stands for Takagi Sujino Kong.
Okay.
TSK is actually much more computationally efficient because it skips that visual center of gravity step entirely. Defuzzification is built directly into the rules using polynomial or linear functions.
Meaning, instead of the computer having to draw a graph, plot overlapping triangles, and calculate a physical balancing point, it just runs a direct algebraic math formula to spit out the final number.
Precisely, which is why it is fantastic for algorithmic optimization and machine learning. I mean, it saves massive amounts of computing power.
Right.
But it is much less intuitive for a human programmer to visualize or troubleshoot. Mamdani remains popular because it translates human thought into machine action in a way we can actually picture in our heads.
Okay, I have to imagine you listening to this might be having the exact same thought I had when I first started reading these sources. We are talking about assigning values between 0 and 1. And a 20% chance of rain is 0.2. So what is the actual difference between fuzzy logic and standard probability theory? Aren't they the exact same thing?
It's a completely natural assumption, and honestly, it's one that actually sparked a massive academic turf war.
Really, a turf war over math.
Oh, absolutely. While both fields use the exact same numerical range, so between 0 and 1, they model fundamentally different concepts of reality because probability models ignorance, but fuzzy logic models vagueness.
Here's where it gets really interesting. I want you to imagine you are holding a completely opaque bottle of water. You can't see inside it at all.
Okay, an opaque bottle.
Someone tells you there's a 20% chance that the water inside is totally toxic and an 80% chance it's pure mountain spring water. That is probability. The bottle is full. The water has an absolute binary state-like. It is either pure or it is poison, but you are entirely ignorant of which one it is until you drink it.
And because you are ignorant of the state, probability measures the frequency or likelihood of an event occurring in the future.
Exactly.
Now contrast that opaque bottle with fuzzy logic.
Right. Now imagine a clear glass bottle. You can see perfectly inside, with 100% certainty that it contains pure, safe drinking water. But the bottle is only 20% full. There is no ignorance there. You know exactly what it is. The state of the bottle's fullness is simply a matter of vagueness or degree. It is a partial truth.
And because you can clearly see that it's 20% full, the mathematical tools you use to interact with it completely change. This distinction is exactly why fuzzy sets were developed at Berkeley in the mid-20th century. Traditional probability theory simply could not model uncertainty and vagueness jointly.
It just didn't work.
Right. Probability forces you to guess the state of a hidden system, while fuzzy logic allows you to measure the state of a vaguely defined system.
But the text mentions this massive academic debate over this exact distinction. There was a prominent researcher named Bart Kosko, and he argued that probability is actually just a subtheory of fuzzy logic. He went so far as to mathematically derive Bayes' theorem, which, is basically the holy grail formula of probability.
Yeah.
Entirely from the concept of fuzzy subsihood.
He did, essentially arguing that the likelihood of something happening is just a specific slice of the broader mathematics of vagueness.
Yeah.
But on the other side of the aisle, Lotfi Zadeh, the father of fuzzy logic, he argued the exact opposite. He maintained they are entirely different in character. Zadeh even created something called possibility theory as a generalization to handle the types of uncertainty that probability mathematically failed to capture.
Possibility theory.
Yeah, it really forces us to ask a profound question about how we view the world. Like, how often in our daily lives do we confuse our own ignorance of a situation with the inherent vagueness of the situation itself?
That is so true. We try to put betting odds on things that aren't actually events waiting to happen. They're just realities that exist perpetually in the gray area. So we have this profound philosophical distinction, and we have the clever math of fuzzification and the center of weight calculation. But, what does this actually do in the real world?
Oh, it fundamentally runs the modern world. Many of the earliest and most spectacular successes of fuzzy logic actually happened in Japan during the 1980s.
Yes, the Sendai subway system.
The Sendai Subway 1000 series. So before fuzzy logic, automated trains used really rigid binary rules. A computer would literally say, if speed is over 50, apply 10% brake.
Which sounds awful.
It was. The result was a jerky, uncomfortable ride as the train constantly toggled between absolute states. But the Sendai engineers, they implemented a fuzzy system.
Using those hedges.
Exactly. It used those vague rules we talked about, like if you're close to the destination station and moving fairly fast, increase the brake pressure somewhat.
Wow.
The system processed all those overlapping conditions continuously, and the result was a train that accelerated and stopped so smoothly and with such microscopic precision that it vastly improved ride comfort and fuel economy.
And the source text lists so many everyday applications that followed that, like the anti-lock brakes on your car. They map the temperature ranges and speed of the brake pads to fuzzy truth values to constantly adjust the braking force so you don't skid.
Yeah.
Or washing machines that use a single button to figure out exactly how much water and agitation you need based on, fuzzy readings of the load weight and dirtiness.
It's everywhere.
Sony even used it for handwriting recognition in early pocket computers because human handwriting is basically the ultimate vague data set.
It really is. And if we connect this to the bigger picture, beyond just watching machines in subways, the most vital application of fuzzy logic today is the foundation of artificial intelligence.
Wait, really? Because isn't AI all about massive databases and binary code?
Well, at the hardware level, yes, computers process ones and zeros. But at the architectural level, the underlying logic of modern neural networks, which are the systems actually driving the current AI boom, that logic is fundamentally fuzzy.
The text actually mentions a really pivotal moment in the 1980s for machine learning. Researchers were divided into two main camps. One camp was using what's called decision tree learning.
Right, and decision trees use strict binary logic. Imagine a flowchart. The computer looks at a pixel and asks, is this pixel dark? If yes, go down the left branch. If no, go down the right branch.
Careful enough?
It forces a rigid either-or choice at every single step, and it perfectly matched the computer hardware of the time.
But the other camp used neural networks.
Ugh.
And despite binary logic seeming like the obvious choice for a computer, the neural networks won out.
They did.
Why? Because the real world doesn't operate in zeros and ones.
Exactly. The mechanism behind a neural network's success is that it doesn't force an immediate binary choice. A neural network takes a huge variety of inputs. If a pixel is 40% dark, it doesn't force it to be a 1 or a 0.
It just accepts it as 40%.
Right. It takes that zero point 0.4 value, assigns it a numerical weight, and passes that intermediate value forward to the next layer of the network. It carries the nuance of the gray area through the entire system without ever dropping it.
That's brilliant.
Neural networks resulted in much more accurate models of complex situations precisely because they embraced the fuzzy nature of the data.
Which totally brings us back to that MRI example from the beginning.
Yeah.
Medical decision-making is a massive frontier for fuzzy logic because medical data is incredibly subjective. Like a patient says their pain is a 7 out of 10.
Yeah.
Or a doctor is looking at an image trying to find the edge of a brain tumor.
An image-based computer-aided diagnosis relies heavily on fuzzy sets. When you look at an MRI of a tumor or a photograph of an infected wound after surgery, the pixels don't suddenly turn from healthy tissue to tumor in a perfectly crisp, mathematically straight line.
It's a gradient.
It is a gradient. The boundary is fuzzy. By using fuzzy logic, the computer can analyze the biomedical signals and segment those images by recognizing degrees of membership. It says, this pixel is 80% tumor, 20% healthy tissue.
But the text points out a beautiful, almost tragic irony in this pursuit. It notes that the envelope of what can be achieved and what cannot be achieved in medical diagnosis, ironically, is itself a fuzzy one.
Yeah. The underlying challenge is that we are trying to mathematically map human subjectivity. We rely on humans to define what healthy or sick looks like in the first place, and there is an inherent mathematical limit to how perfect that translation can ever be.
Wow.
And this limitation actually extends far beyond medicine. The computational theorist Leslie Valiant coined a brilliant term for this. He called them ecorhythms.
Ecorhythms. Algorithms that learn from their complex environments, like your ecosystems.
Exactly. Valiant argues that machine learning is essentially evolutionary biology playing out in code. Ecorhythms share fuzzy logic's core philosophy. They focus on possibilities rather than exact probabilities.
Wow.
They are designed to generalize, to approximate, and simplify logic in environments that are simply too chaotic, too noisy, and too complex to understand perfectly or discretely. They survive by adapting to the gray area.
So what does this all mean? When you step back and look at the whole picture, there is this incredible, almost poetic irony. The crispest, most precise, most reliable systems we rely on every single day. From the anti-lock brakes keeping us from crashing, to the medical imaging saving lives, to the AI recognizing our voices, they actually require fuzzy thinking to function flawlessly.
It's a huge paradox.
In order to be exact in the real world, the machine must first learn how to be vague.
It represents a profound paradigm shift in how we approach problem solving. We literally had to teach Silicon to understand the spectrum of human intention.
So to wrap this up, we've gone on quite a journey today. We started with Lafayette's 1965 rebellion against the rigid binary Boolean logic that defined early computers.
We did.
We walked through Mamdani's rulebooks, learning how overlapping triangles and center-of-weight calculations turned words like somewhat and rather into precise mechanical voltages.
Yes.
We rode the buttery smooth Sendai subway in Japan, and we peered under the hood of the neural networks, carrying partial truths through the modern AI revolution. It's all built on the math of the gray area.
And as we close, there's one final lingering idea drawn from the decidability issues section of the source text that I really think is worth reflecting on.
Okay, let's hear it.
The text notes an unresolved, open question in mathematics regarding whether Kurt Gödel's famous incompleteness theorems can be extended to fuzzy logic.
Ah, Gödel. So for those who might not spend their weekends reading theoretical math, Gödel basically proved that in any complex set of mathematical rules, you will eventually find statements that are 100% true, but the rules themselves are fundamentally incapable of proving them. The system is always technically incomplete.
Which is just a staggering reality for mathematicians to accept. Now, apply that to what we've learned today. I want to pose this directly to you, listening right now. If human reasoning is fundamentally fuzzy, as we've discussed, and if fuzzy logic itself is eventually proven to be bound by those Gödelian limits of what can ever be mathematically proven, are there fundamental truths about your own life, about human nature, and about our universe that aren't just currently unknown to us, but are mathematically destined to remain in the gray area forever?
Wow. Destined to be gray. Even the math admits it can't know everything. Well, on that note, we want to thank you for joining us on this deep dive. The next time you sit down to your computer, or you hit the brakes in your car, or you just try to describe the color of the sky, remember that the world isn't a light switch. Look at the somewhats and the rathers of your own day in a whole new mathematically brilliant light. Embrace the dimmer switch. Thanks for listening.